Hi, this is the second video in this series about large language models and how they work. So, if you hopefully had a chance to watch the first video in this series, this is the second. All right, slide advance. So, how do large language models work? Why should we care how they work? So I think about this kind of in looking under the hood of a large language model. And in the analogy here, you certainly can drive a car without knowing how the engine and other parts work. However, sometimes they don't work. And it's helpful to know if something isn't working, to know what you're talking about and if you fix it yourself or not. If you want to explain something to a mechanic, it's very helpful to know kind of what the pieces are. So in this video, we're going to talk about some of the pieces of a large language model, how they go together, how they're constructed. Why don't things work sometimes? Well, sometimes it's interesting to see, frankly, that they do work, and other times it's interesting to see that they don't work. What are large language models good at? We'll talk about this. We talked about this in the last video and talk about it a little bit more now. And what are they not good at? So if we understand how large language models work, one thing it can do for us is it can help us know their limitations so that we can use them in appropriate ways that will be productive in giving good results. All right, so from our prior video, there are various types of generative AI models, generative meaning that they create new content. There's large language models, which take language of a particular type and convert it into other language. So that language could be English that's translated into English by questions and answers. It could be English translated into some other language like German. It could be computer languages. It could be meeting transcripts, things like that. So they basically act on text. The other type of generative AI models are, I shouldn't say types, it's multimodal models. Multimodal meaning that it does a lot of different types of data in and out. It could be, for example, image generation, which would be text to image, or image recognition, image to text, and so forth. All right, some of the building blocks we have for these AI models, for any of these AI models, the most fundamental building block is called a perceptron. And they are organized into what we're going to call an artificial neural network, or a multi-layer perceptron. And please don't get hung up on the terminology too much. We will, I'll try to go through these and explain them, and then also provide a terminology sheet. Perhaps I'll post that in the comments down below, or in not the comments, the description. Okay, so here's an example of a perceptron, and basically this is kind of crazy, but the perceptron is comprised of inputs, which are numbers, and there's some different inputs that go in, and those inputs are multiplied by a weight, and the weight tells how much each input influences the value of the perceptron. So here are some weights that have been set. And this image shows these weights moving. This is called the training process, is that we train the model to understand things, and the way we do that is we adjust the weights. So there's weights. There's a thing called a bias. I'm not going to go into details about what that is. So basically, we take the inputs and we multiply them by some weight values and sum them together. So it's a weighted sum. We add in the bias, and the result is the output value that goes through the activation function. The activation function says, well, if the weighted sum plus the bias is greater than some value, then the activation is positive. It could be near 1, or it's below some value, it's maybe negative, near -1. This activation function shown in this particular image here is not the most common. There are other ones that are more common, so I won't go into the details about that. But the idea is that we have some values coming in, and some combination of values will cause the output to be either positive or negative. And crazy as it may seem, this is really the fundamental building block of even the most advanced reasoning models that we have at this time of recording this video in 2025, the end of 2025, which is transformer architecture. So what we do is we take these perceptrons and we take a whole bunch of them and combine them into an artificial neural network where we have a bunch of numbers going in and they pass through the network through a bunch of perceptrons in layers. And so there's the first layer, the second layer, the third layer. This is a very simple example. The reality is that these multi-layer perceptrons in a given large language model might have, 100 layers, or potentially many more than that, because we tend to do things in parallel with this. So we just basically have a bunch of weights, a bunch of values that go through those weights, a bunch of biases, and then pass it through. So here we have an input layer, we have the hidden layers, they call these, and we have the output layer, the artificial neural network or multi-layer perceptron. These weights are also called parameters of the model. So we're going to talk about how big models are, and big models have trillions of parameters. Small models have mere billions of parameters. There are some that actually have millions of parameters that have come out in recent months that, they actually work. But the smartest, if I could call it that, the smartest models typically have trillions of parameters. All right, so we have this artificial neural network, and this is a dramatic oversimplification because there's a lot of pieces to this, but that we'll talk about later. But basically, we start out wanting to train the parameters or the weights of this artificial neural network, and the way that we do that is we have a corpus. The corpus is a massive amount of data. In the case of large language models, it's text data. And we're going to use that as the basis of training this model. So in a corpus, a common example is one called the common crawl, which is basically a mirror image of the internet. A lot of information. Probably more relevant than that is things like Wikipedia. So a lot of companies use Wikipedia to train their artificial neural networks, their AI models. And basically, we have all the information in Wikipedia and all the connections between words and topics and sentences and paragraphs and things like that. And that was used in the training corpus. So what we do is we pre-process this. We take this corpus and then we first have to tokenize it. So AI models, large language models, this multi-layer perceptron does not understand words. All it understands is numbers that are weighted sums. You cannot multiply a word by a number. Well, I guess you could if the word was TWO over 2. You could multiply that by THREE, but that's kind of not what we're doing here. We're actually doing mathematics here within the multi-layer perceptron. And so we tokenize, we basically, any given word, or sometimes a part of a word, becomes a token. I'll come back to this later. But it's basically, we have to turn the words into numbers. Then, with those numbers, we look up in an embedding table this thing called an embedding, which is a vector of meaning. It's basically a bunch of numbers. So for any given token, we will have a list of maybe 1,000 numbers that represents the meaning of that word. We have to get to semantic space. What that means is we have to talk about meaning. So what these large language models do is they take these words that we feed them from the corpus, we tokenize them, then we use the tokens, we look up the embeddings, and the embeddings tell about the meaning of those tokens. I'll talk more about that later, as I said. Then we get the results out of the model, which are a bunch of numbers, and we say, was this the results we expected based on what was in the corpus? And if it wasn't as we expected, and it usually isn't, we backpropagate, which basically means we go back and adjust the parameters or the weights so that next time they'll do a better job of producing the output that we want. So a simple example of that could be, let me just think of a common sentence. Happy birthday to you. So happy birthday to you, if I said, happy blank to you, what would go in the blank? So in training, maybe the corpus might have the phrase, happy birthday to you, but what it would do in training is it would eliminate one or more of the words. It might eliminate the word birthday. So it feeds into the model, happy something to you. It's a bag of words with something missing. And then it's trying to predict the missing word, which is birthday. And this is, again, a dramatic oversimplification here, but just for the sake of illustrating this concept. So what happens is it tries to predict the missing word, and the output layer, it says the missing word was happy shoe shine. Or is that two words? I don't know. Happy shoe shine to you. That's not right. So what happens is it goes back through the model, the backpropagation, and it decreases the chance the next time it's going to pick shoe shine, and increases the chance the next time it's going to pick birthday. Sometimes, though, you don't say happy birthday to you, you say happy Christmas to you, if you're from the UK, for example. Or you might say happy Hanukkah, or something else. So, what happens is, over time, it takes the corpus and feeds it through, and it recognizes patterns to help predict what the next token is going to be in a particular sequence. That's what we're doing. I'll come back to that as well. So this is unsupervised learning. Basically, we feed the data in, it eliminates pieces of the data and tries to predict the unknown pieces. It's self-supervised. You give it some words, and it predicts the missing words. Then it backpropagates, because it doesn't predict very well initially. All right, then that's how we train the model. That training process costs, for large, what they call foundation models, it costs billions of dollars to do that training. Hopefully those prices will come down in the future. Then, once it's trained, the model still needs to be given some common sense. We do that through the process of alignment. What we do there is we have alignment data. This is labeled. So in the training, the corpus was not labeled data. It's just a bunch of data. And we have to predict missing words. Now we have labeled data, which is that we have flagged as being, right or wrong, or this is a good answer or a bad answer to a question, or how we want the model to behave. And so we have this labeled data, and we feed it into the model. And sadly, this is very expensive to get this labeled data here, because we need humans to do this. It's the humans are, this is called reinforcement learning from human feedback. They basically these companies hire, I don't know how many, probably thousands of people to just sit there at the computer and indicate what's right and what's wrong about responses coming from the model. And that's used to align the model to guide the large language model's behavior. It reduces things like toxicity. What is toxicity? That's things like, swear language, or it can be telling people bad things like, go kill your neighbor's dog because the dog is barking, or something like that, So we want to reduce toxicity, content that's not appropriate. So that's why we do alignment. It prevents prompt injection, jailbreaks. I won't go into that. You don't need that details now. Okay, this is called fine-tuning. We fine-tune the model. So first train it, then they fine-tune the model. Then we get to inference. Inference is where we're actually going to use the model. And so we have this trained, or I should say pre-trained data. We have somebody's prompt. We have, with the prompt, maybe some context. So that could be some information that helps with the prompt. And then we feed it into the model, and out comes the results. The result of the model is an embedding, so we have to unembed it and we have to detokenize it. We turn it back into words, and hallelujah, we get the words back, and hopefully those are good words. So we have a question, we say, what is the capital of France? And it has to predict the next word, and it embeds and unembeds at the end. It says the capital of France is Idaho Falls. Okay, That's actually not a token, but anyway, it says something wrong. Oh, okay, that's not likely to happen if the model's been well trained. It's going to say Paris because the model's been trained that when you give it sequences of words or tokens like what is the capital of France, it returns with Paris. Okay, so model architecture. Before 2017, the models, AI models, were rule-based systems. They basically had rules like if this, then this. The programmers would develop these rules. Sequence to sequence, you give it a sequence of data like language in English and it would translate it into French. Recurrent neural networks, they were a neural network where you feed things in, you feed more things in, and that's how they work, so some of the other ways. And in that recurrence, they would have typically a single value, which would be a memory. They would remember what it did. Okay. Short-term, long-term memory. So the problem was the memory didn't last very long, so they had to figure out how to do longer short-term memory for these things. So these were some of the attempts people had before 2017 to make large language models work effectively. And some worked, but a lot of them didn't work very well. After 2017, we shifted to a transformer architecture, which is the G in GPT. GPT is the generative pre-trained transformer. So it's a transformer architecture. How does this work? So this is to kind of reiterate what we've talked about already. We start with a prompt. So this is how in inference meaning we're going to give the model some prompt and some context and some information, and it's going to generate some output. So we give it the prompt, we tokenize the prompt, so we turn it from words into numbers. We do semantic embedding, which I'll come back to. We do positional encoding, we feed it through an attention mechanism, we do a feed forward, we unembed and detokenize. Okay, so let me take you through these just kind of quickly here. The prompt, it could be something like create a list of elements of a transformer AI models and give examples of each. Okay? We also might have instructions that go with this. Things like you're a helpful assistant or provide the response in Italian or whatever. Okay? Provide a narrative format. After providing an answer to the user, ask follow-up questions. So there's system instructions. In some models, you can set the system instructions, but for a lot of models like ChatGPT, OpenAI provides the system instructions. They actually dictate how the model will respond to you. Okay? The entire conversation is fed into this. Okay, I'll come back to that later. All right. AI models are math models. We have to tokenize, as I mentioned. They only understand numbers. They don't understand words. So every word is one or more numbers. Okay? There's a tool here that students in my class can have a chance to, we'll do a little exercise with it. But the phrase, Professor Sampson wasn't a professor at UVA. I wasn't a professor there. I was a student there. That actually is 11 tokens. Professor is a token. Samp is a token. Son is a token. Wasn't is a token. Apostrophe T is a token. And so forth. This is based on one tokenization scheme from, it's a kind of an older one. GPT 3.5 and GPT 4. May they rest in peace. Okay, so we turn tokens. Then we do semantic embeddings. Basically, tokens are just a bunch of numbers, but the token numbers don't really mean anything yet. So for example, in one embedding, or one tokenization method, the number 27941 represents the word pizza. The token 27942 is an exclamation mark, 43 is pregnancy, 44 is assert in capital letters. It's kind of weird, but these numbers really don't have any. The pizza and exclamation mark, although I guess sometimes we can be excited about pizza, especially if we have cravings of pregnancy and we want to assert our hunger. But the tokens are kind of meaningless. So what we do is we create semantic vectors. Okay, not this vector here. That's a different vector here. But we create a semantic vector, which is just basically a list of numbers that represent the meaning. I'm not going to go into details of that. In my other writing, you can read more about that. Okay, positional encoding. The numbers, the embeddings go into the model at one time, every one. So even if you give it 10,000 tokens, all 10,000 are converted to embeddings and they all go into the model simultaneously. That's how transformer models are able to do what they do, is the fact that we can do parallel processing and feed everything in at once. And it can work on it in parallel. That's very important. Okay, so here we have a bag of words. Bad, explain, for, food, good, health. We could organize it different ways. Explain why good tasting junk food is bad for your health, or explain why bad tasting junk food is good for your health. Those are very different sentences based on the meaning. So basically, in a nutshell, what they do is positional encoding. They basically tweak each embedding so that the model will know where it exists in sequence. And it does it through this thing called sinusoidal positional encoding. I'm not going to go into that here, but just trust me, it works. Then, believe it or not, there's more. The positionally encoded embeddings go into an attention mechanism that identifies interrelationships between words, identifies which words relate to other words, identifies words that modify other words. Here's an example. The animal didn't cross the street because it was too tired. Okay, what is it? The animal or the street? It's actually the animal. Streets don't get tired. The second sentence is the animal didn't cross the street because it was too wide. Animals could be wide, but usually we're talking about streets. Streets, that's a characteristic of streets. So attention mechanisms basically help us understand what words are relevant and relate to other words. Then we go through a feed-forward network, just basically a bunch of perceptrons there, a lot of them. Look for patterns in the data. This is called feature detection. That is the main function of any of these AI models, is to do feature detection, to identify patterns, features that are useful to know about in the data, and how the input patterns relate to appropriate output patterns. That's what we're doing. Okay, this repeats here. Feed forward attention mechanism. There's multi-head attention mechanisms. It's kind of complicated, but there's a lot of these things. Layers of feed forward networks. A lot of these things, again, in parallel. Here's some pictures representing this. I'm not going to go into the details of this, but this was a bunch of numbers from a neural network trying to predict something having to do with, I think, a Harry Potter something, because the answer that it came up with is Snape or Trelawney or Quirrell. And so I don't know, I don't think that Trelawney is actually represents a token there. So that's kind of a little deceptive here. But anyway, you're trying to predict tokens is what the goal is. Find the tokens most like the output embedding. So we do the unembedding, and then the detokenization is to basically give us words because we like words as humans. All right, then we take the output. This is one run through this to predict one token. We take the output and then we feed it back in to start all over again. So for example, I could feed into a large language model, who is Elvis? And it would respond with, first, a single token, Elvis. Then, what comes after Elvis was? Elvis was. Then what would come next? It feeds it all through this whole process again. A. Then it feeds all this in through the whole process again. Singer. And so forth. Now, the key to this is called, autoregression. If you use a large language model, you'll notice it does not produce all the output at once. It produces it kind of word by word, actually token by token. And it kind of feeds you this, a token at a time or a few tokens at a time. If you use the models in what they call streaming mode here. So basically, that's how they work. It's kind of amazing, but it just really produces one at a time. This, as was mentioned in the prior video, is called the stochastic parrot. So it basically says this idea that the model predicts tokens based on what the model has seen in the training data and the inference context. Okay? So, then how can it be so smart? If all it's doing is predicting tokens, how can it appear to be so smart? Well, they are smart. AI versus human performance on various tests. AI far can exceed human performance on various tests. It's pretty amazing. How do they get so smart? Well, that you're going to have to stay tuned for the next video. That's the topic of the next video. So we'll see you then.